In this pre-lecture, we're going to wrap up some things on modular arithmetic and introduce primitive roots, which we'll be doing some more stuff related to that next time. So we use a special notation here to denote the integers modulo m. So we usually say this z mod m. And this denotes the integers modulo m, so we'll usually think about this as 0 up through m minus 1 with modular operation, so with the modular addition and multiplication that we've been talking about. But it's important to remember when working with z mod m that each number in this list represents infinitely many integers. So in z mod 6, for example, when we write 2, that's the same as 8 minus 4, minus 10, etc. We're just kind of grouping all of those numbers together because they're the same thing modulo 6. So even though we'll write only 0 up through m minus 1, keep in mind that each of those is representing lots of different numbers as well. And recall that an integer b is a multiplicative inverse for a mod m if a times b is congruent to 1 mod m, and then we'll write b equals a inverse mod m. So something that we touched on a little bit in class today, but hadn't formally gone through yet, is that a is a multiplicative inverse modulo m if and only if a and m are relatively prime. So this is a simple way that you can tell if an element has a multiplicative inverse mod m or if it doesn't. This is an if and only if statement, so we're going to have to prove both directions, and for both directions we're going to use this fact that we've talked about before when we were looking at things being relatively prime and greatest common divisors, which is that a and m are relatively prime if and only if there exist integers x and y such that xa plus ym equals 1. So this fact has already come up a couple of times in doing proofs. It's a really handy thing, and it's useful again here. So let's start by proving the forward direction. So let's say if A has a multiplicative inverse, mod m, so that means that there exists some b such that a b is congruent to 1 mod m, and then that means that m divides ab minus 1, and that in turn, using our definition of divisibility, that means that there exists k such that m k equals a b minus 1. And now we can reorganize this to b1 equals ab plus minus km. And so by our fact, this is equivalent to a and m being relatively prime. So a and m are relatively prime. So maybe this is a good time to note that when I'm writing proofs in these lecture slides, you'll notice I use a lot of abbreviations and kind of partial sentences, things like that. You should write out the words and use complete sentences in your proofs. I just don't want to sit here forever while I, slowly write out complete sentences and you're sitting there bored watching the video. So keep that in mind in your proofs, that I'll get all of the important points there, but, my writing in these pre-lecture proofs in particular isn't going to be where I would want it for write-up for a formal proof. All right, that said, in the reverse direction, we're going to have if a and m are relatively prime. By that fact, again, there exists integers x and y such that xa plus ym equals 1. So then we can solve for ym there, and ym equals 1 minus xa. And so we're kind of doing the same thing that we did in the previous direction, just backwards now. And that means that m divides 1 minus xa, and then by the definition of congruence modulo m, we've got 1 congruent to xa mod m, so a has a multiplicative inverse mod m. So that completes that proof there, and this can be a really handy test if you're trying to figure out if something has a multiplicative inverse or not. And you can also use this to figure out what that multiplicative inverse is, because you'll notice once we write xa plus ym equals 1, then it turns out that x works for a multiplicative inverse. So you can use that to find multiplicative inverses as well. All right, so we talked about z mod m being the integers modulo m, and now we define z mod m cross, so that's a little times symbol up there. Not in x. And this is the set of A in Z mod M such that A has a multiplicative inverse mod M. Like we showed in the proposition, this is the same as the set of A in Z mod M such that A and M are relatively prime, or such that their greatest common divisor is 1. So we call this the group of units, or the multiplicative group in Z mod M. So here we're looking at things that have multiplicative inverses and just listing those off. So in Z mod 6, when we're looking for things that have multiplicative inverses mod 6, we want things that are relatively prime to 6. And since we're, kind of limiting ourselves to things between 0 and 5 because everything is congruent to one of those, then we're just left with 1 and 5 as our group of units there, and remembering that each of these is representing lots of different integers, so 1 is the same as 7, same as 13, etc. So even though we've just got 2 things here, each of those is equivalent to infinitely many integers. Then looking at the group of units in Z mod 9, we're looking for things relatively prime to 9. So that would be 1, 2, 4, 5, 7, 8. And in Z mod 11, we're looking for things relatively prime to 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 are all congruent, or all have multiplicative inverses mod 11. So notice here we've got this prime number, which means that everything except for 0, between 0 and that number minus 1, are going to be relatively prime to that number. So all non-zero elements in Z mod M here have multiplicative inverses. So that's an important fact when we've got a prime number. So notice I called this group of units, or a multiplicative group. So groups are something that we'll be talking about next week, and defining those in general, so what exactly we mean by a group. So going back to my note about this special case when Z mod P where P is prime, where we said that everything that's non-zero has a multiplicative inverse, it turns out that Z mod P is this special structure which we call a field. And the operations here are modular addition and multiplication. So what we mean by a field is that it has these 10 nice properties that make arithmetic work really nicely. So addition should be associative, so we can regroup and add things in different orders like that. Multiplication should also be associative, so we can regroup. Addition and multiplication should both be commutative, so we can change the order, and x plus y is equal to y plus x. X times y equals y times x. We should be able to distribute multiplication over addition, so x times y plus z should be x times y plus x times z. There should be an additive identity, so there should be some element so that when we add it to all the other elements, we just get that element that we added it to, so that's 0. We should also have a multiplicative identity, so an element which we'll call 1, so that when we multiply it by other elements, we just get the other element that we multiplied it by. And then we should have additive inverses, for any x in the field, there is some other element so that when we add them together we get back to 0, the additive identity. And similarly for multiplicative inverses, as long as you've got something that's not 0, we should be able to find something else so that when we multiply them together we get 1. And finally, 1 should not equal 0. So essentially this ends up meaning that a field can't just be 0. So I don't expect you to be an expert on fields after going through and seeing these 10 properties one time. We'll be talking about fields a lot more thoroughly later, after we've talked about groups and after we've talked about rings. So this is sort of a preview of what's coming, and kind of notice that Z mod P has all of these properties when by equals we mean congruence modulo P, and the plus operation is modular addition, and times is modular multiplication. So these properties should be somewhat familiar because they're things that are true about these modular operations in Z mod P. So far we've talked about addition and multiplication modulo m, and talked somewhat about subtraction, and then how division acts really strangely. So there's another operation we're going to talk about modulo m, which is taking powers. So if n is a positive integer, we define a to the n to be a times a times a times a n times mod m. So notice here that this definition, we're only making this when n is a positive integer, because we can, it has to be a whole number and a whole positive number for us to actually do this and multiply a times itself n times. So for that to make sense, it has to be a positive integer. So for example, when we're computing 2 to the third mod 5, we're doing 2 times 2 times 2. So that would be 8, which is then 3 mod 5. If we're doing 7 squared, we're doing 7 times 7, which is 49, which would then be congruent to 9 mod 10. So remember this when we are dealing with powers modulo m. We're just thinking about multiplying that base times itself a bunch of times, and that's what that power is doing. So we have to be really careful with how we work with powers that are not positive integers. So negative exponents only make sense when the base has a multiplicative inverse, because by a to the minus 9, so in normal arithmetic, by this we'd mean 1 over a to the 9th, but because we're not doing normal division modulo m, that gets replaced with a multiplicative inverse. So this would mean a inverse to the 9th. So this only makes sense if a has a multiplicative inverse. So only if a inverse exists. And the case is worse when we consider non-integer powers. They aren't well defined in modular arithmetic. So for example, if we look at 3 squared, we get 2 mod 7, and if we get 4 squared, we also get 2 mod 7. So if we're trying to figure out what the square root of 2 should be mod 7, there's not really a clear choice between those two. So this is not clear what that should be, so we don't want to write things like 2 to the 1/2 because that's ambiguous. So don't write this. One last topic for the pre-lecture here, an integer g, which is relatively prime to m, so it's in that group of units. We call that a primitive root modulo m if for every x that's also relatively prime to m, so also in the group of units. There is an integer L such that g to the L is congruent to x mod m. So what this means is that by taking powers of g, we can get all of the elements of the multiplicative group. So for example, if we're looking in z mod 5, then the elements in the multiplicative group are 1, 2, 3, and 4. So we're going to be looking to see if we can get all of those as powers of elements. So let's start by looking at 1 and figure out if 1 is a primitive root. So if we do 1 to the 1, we get 1. 1 squared is also 1 by doing 1 times 1. 1 cubed is 1. So on and so forth. We're always going to get 1, so we don't get everything in z mod 5 cross, so then 1 is not a primitive root. If, on the other hand, we look at 2, we've got 2 to the 1 is 2, 2 squared is 4, 2 to the 3rd is 8, and then that's congruent to 3 mod 5, and 2 to the 4th, that's 16, which is congruent to 1 mod 5. So we've gotten everything 1, 2, 3, 4 as powers of 2, so that means that 2 is a primitive root. Now let's look at 3. 3 to the 1 is 3. 3 squared is 9, which is 4. 3 to the 3rd, so we can do 4 times 3, which is 12, and then that's 2. And 3 to the 4th, we can do 2 times 3, which is 6, which is then 1. So we also see that 3 is a primitive root. And finally, looking at 4, 4 to the 1 is 4, 4 squared is 16, which is 1. 4 cubed, we can do 1 times 4, so we get 4. 4 to the 4th, we do 4 times 4 and get 1 again, and we're just going to keep alternating back and forth between 1 and 4, so we never get 2 or 3. So 4 is not a primitive root, mod 5. These are all specific to mod 5. They might be primitive roots. Mod other things, well, 1 will never be a primitive root, except mod 2, I guess. So now looking at another example here in z mod 6, so our group of units is just 1 and 5 since those are the only things relatively prime to 6. So checking for a primitive root, if we do 1 to the 1, we get 1. 1 squared equals 1. 1 cubed equals 1. We're always getting 1s there, so 1 is not a primitive root. Mod 6. But if we look at 5, 5 to the 1 is 5, and 5 squared is 25, which is 1 mod 6. So we've gotten both 1 and 5, so we've gotten everything in the group of units, so that means 5 is a primitive root. Mod 6. So you'll notice here that I've already started fudging, writing congruence mod 5 or mod 6 for everything. When the context is clear, I'll typically just write equals. When I know, or it's clear that we're working inside of Z mod 5, I won't bother writing that congruence every time, and I'll assume that you know what I mean when I'm writing, things that are equal because we're working inside of Z mod 5. And that'll be consistent as we're moving into this pure math section, going into groups, rings, and fields, that equals and whatever operations that we're working with, it's understood that those are the equals and operations specific to whatever structure we're working inside of. So that will be more clear later. All right, so make sure you answer the pre-lecture questions, and that's it for this one.